Welcome to the Deep Dive, where we try to give you that shortcut to, well, really understanding complex topics. Today, we're jumping into something that honestly still feels a bit like magic to a lot of people, artificial intelligence, especially generative AI. I mean, if you've used ChatGPT, typed in a prompt, watched it to create text, or made an image from words, you know that feeling? It's like having this incredibly brilliant, almost kind of whimsical chef in your computer ready to cook up whatever you ask for. But how do we actually get from that really cool user experience to the raw code, the actual ingredients, the structure that makes it all work? That's where AI engineering comes in. We're going beyond just using AI. We want to understand how you build it, how you deploy it, and crucially, how you keep improving these incredibly complex systems. So today, our mission really is to pull back the curtain on that intricate kitchen, get straight to the most important stuff, and give you the ultimate cheat code, if you will, to understanding how these digital brains are built and kept running.
Exactly. We're going to try and cut through all of that complexity, pull out the key insights, and give you, a real shortcut to being properly informed about the whole life cycle of an AI application. Think of us as your guides through this AI kitchen. We'll cover everything from the tiniest building blocks right up to the big picture architecture.
Okay, so let's get into it. When we look inside these AI models, like right down at the most basic level, what's the first thing we find? We're going to start with tokens, right?
That's exactly right. Tokens. They're basically the smallest pieces of text that the language model actually deals with. Could be a single character, could be a whole word, or sometimes just, part of a word. So like GPT-4 takes, I can't wait to build AI applications and breaks it into 9 tokens. Just can't becomes 2 tokens. Can and tiki. And that tokenization, it's really critical, not just for efficiently representing text or making the vocabulary smaller. But here's the thing, these tiny pieces, they can subtly influence the AI's biases, even its creativity. Think about it. If a model sees unbelievable as unbelievable, it processes that differently than if it was just one chunk.
Huh. I hadn't thought about it like that.
Yeah, that tiny difference, that granularity, it can shape how it understands things, maybe create blind spots or, sometimes sparks of something unexpected. It's like breaking a recipe down to the absolute smallest ingredient.
Okay, so tokens are those fundamental ingredients, but how does the AI take those bits and pieces and, understand what they mean, the relationships, the context? Yeah. How does it figure out king relates to queen differently than, say, apple to orange? That's embeddings, isn't it?
Precisely. Embeddings are the model's internal way of representing that input data. Think of them as these high-dimensional numerical vectors, basically a long string of numbers. And the key thing is, words or concepts that mean similar things end up close to each other in this number space.
So it's like a map of meaning, but with numbers.
Exactly. And the magic isn't just that they represent meaning, it's that they turn abstract ideas into something a machine can actually sort of feel and calculate with. They're kind of the silent architects behind almost every recommendation engine you use. Spotify uses them for songs, YouTube for videos, Pinterest for image search, even Netflix uses them internally for deciding on content. And well, when they go wrong, they're also behind those weird, irrelevant suggestions you sometimes get, like a chef confusing salt and sugar just because they look similar.
Right. Okay, that's a powerful concept. So we have the ingredients tokens and the way the AI understands their flavor and relationships embeddings. But how does it actually learn from all this? How does it refine its understanding over time, like that chef tasting the soup and adding more salt? This sounds like Bayesian training methods.
Yeah, the Bayesian training is a really powerful statistical way to do this. It uses something called Bayes' theorem. In simple terms, it lets the model constantly update how likely it thinks a hypothesis is as it gets more evidence, more data. So the model starts with some initial ideas, previous beliefs, you could say. Then, as new data flows in, it refines its predictions by mixing that new info with what it already thought.
So it's always learning, always adjusting.
Exactly. But the real breakthrough with Bayesian methods isn't just updating beliefs. It's that it lets the AI model uncertainty. It can say, okay, here's the answer, and here's how confident I am about it, which is super important for high-stakes stuff.
That makes sense.
And this whole iterative process, refining predictions, it's how it learns. And all that refined understanding, all those complex numerical representations, it gets packed into the AI's brain, often a file called a PyTorch Tensor File. That file is the machine learning model you can deploy. It's ready to go.
Okay, so we've got the core brain, the model file. But actually, building AI isn't just about the model, is it? It's the whole software development process around it. How do modern teams actually approach building something this complex? How's it different from, say, how software used to be built?
Oh, it's hugely different. In the old days, software was often treated like building a bridge. You'd have these fixed plans like the waterfall method. You'd plan everything up front and then just execute.
Stick to the plan no matter what.
Pretty much. Don't change the plan if you don't know that you're stupid, was kind of the mindset.
Right.
And honestly, that rigid approach led to what people called the software crisis of the 1970s. It's like planning this perfect 5-course meal, right? Only to find out halfway through cooking that your main guest is allergic to gluten.
Right. Disaster.
Exactly. Agile, on the other hand, it embraces change. It's built on the idea that as you work on something, everyone learns more. The developers learn about the tech. The clients learn more about what they actually need in their business domain. So Agile says, let's continually change the plan. It focuses on flexibility, talking to the customer constantly, and delivering working software quickly and often. Much more like a chef tasting, adjusting, getting feedback as they go.
That makes sense. And if you're constantly adjusting and collaborating, keeping everything organized must be critical, especially with potentially lots of chefs involved. What tools do teams use to manage all the code that's always changing and the project itself?
Yeah, absolutely crucial. For the code itself, you rely heavily on source code management systems, SCMs, things like Git, maybe Bitbucket, or older ones like SVN. They're essential. They track every single change, keep a full history. It's like your kitchen's master recipe book, logging every single tweak.
Okay, so that's the code history. What about managing the actual work, the tasks?
Right, for project management, you've got tools like GitHub, ZenHub, Trello, JIRA, lots of options. But actually, the combination of GitHub issues, which is built into GitHub where the code often lives, and a tool called ZenHub, that's really powerful. It basically gives you a full-on agile project management system right there. You get sprint backlogs, Kanban boards. Makes it way easier to see who's doing what, manage the workflow, make sure everyone knows what dish they're prepping.
So you've got the code managed, the tasks managed, but how do teams keep track of progress in real time? How do they know if they're on schedule, see the bottlenecks?
Good question. You can actually connect tools like Power BI directly to, say, GitHub. And this lets you build these real-time dashboards for sprint analytics. You can visualize all sorts of key things, like sprint velocity, basically, how much work the team's getting through each sprint. You get an issue status overview, what's open, what's closed. You can see the team workload, who's got what assigned, and even track cycle time, how long tasks are actually taking from start to finish. It's like having a live display in the kitchen, showing order status, who's busy, and how fast things are moving.
Okay, that's pretty sophisticated tracking. So the recipe is refined, the ingredients are managed, progress is tracked. How do we get the finished dish out the door quickly and reliably? Especially with AI, you want to roll out updates fast without, messing things up. This is where CI/CD comes in, I assume.
Exactly. Continuous integration and continuous deployment, or CI/CD. It's all about automating the whole pipeline, building the software, testing it, and deploying it. Tools like Jenkins, Travis CI, Circle CI are common here. You might use something like GitLab CI/CD defined in a YAML file. That file basically lays out the stages. Build might install things. Test runs automated checks for errors. Deploy pushes it live. Automating all this drastically cuts down the time it takes to get new features out the time to market, and it catches conflicts between new code and old code early. So you get these rapid, reliable updates. It's like having this automated conveyor belt in your kitchen. Takes the dish from prep through quality control tasting right out to the customer, fast and consistent.
Right, automating the delivery. Okay, so we've built the kitchen infrastructure. We're writing the recipes using Agile. But let's talk about the ingredients again, the data. You hear data is the lifeblood of AI all the time. But what actually makes data good data for AI? Because surely not all ingredients are equal.
You absolutely hit the nail on the head there. Data quality is just paramount, especially for complex AI stuff like chain of thought reasoning.
Chain of thought? What's that exactly?
Oh, right. It's basically teaching the AI to think step by step or show its work when solving a problem, just like a person might. It helps with more complex reasoning. And for that kind of behavior, you need really high-quality data annotations, the labels or examples you feed the model. Good data needs to be aligned. It should match the kind of output you want. It needs to be consistent. Different examples, different people labeling it should agree. And it needs to be diverse, covering lots of different scenarios, especially for general models like chatbots.
Consistency sounds tricky with human annotators.
It really is. I remember one project, we thought our data was perfect, perfectly aligned. But then we realized the annotations were subtly reinforcing this bias we didn't even know we had, just based on the style of the input. It taught us quality isn't just consistency. It's also about really thinking how humans are interpreting things. Inconsistent labels can totally confuse a model.
Okay, so getting high quality, aligned, consistent, diverse data is key. Once you have it, how do you store and manage it all effectively for AI? What are the best ways, especially given the sheer amount and variety?
Yeah, storage is a big one. We often compare things like JSON with traditional SQL databases. For a lot of AI and ML work, JSON often wins out. It's just more flexible with the kind of varied, sometimes messy, complex data structures you often find in AI. Easier to handle changing formats.
So it's better for the development process, too.
Generally, yeah. Better for the CI/CD build process and for the ML data itself because it adapts more easily. And this all ties into the whole big data paradigm shift. The issue is velocity data is just coming in so fast in such huge volumes that humans literally can't keep up with analyzing it anymore. So that sheer speed forces us to hand over more of the analysis to the machines, to the AI systems themselves.
Right, the scale is just different. But what if you don't have enough real-world data, especially for cutting-edge stuff, next-gen AI? Or what if your real data has flaws or limitations?
That's a great question, and it leads us to synthetic data. This is data that's basically generated artificially, either by writing code or even using another AI. You use it to fill the gaps where real data is hard to get, maybe too expensive or too sensitive, or just to increase the sheer amount of data you have.
Can synthetic data actually be better than real data?
Surprisingly, yes, sometimes. It can actually increase data quality in specific cases. Like, imagine generating really complex math problems for training. An AI might be better at creating consistently hard, novel problems than a human expert would be. But there's a really important catch here. It's called model collapse.
Model collapse sounds bad.
It is. It's what can happen if you keep training models recursively on data generated by other AIs. Over time, the models can start to degrade, lose diversity, develop irreversible flaws. It's like a chef who only learns by tasting dishes made by other chefs using the same old recipes, never trying fresh, raw ingredients. Eventually, the unique flavors just get washed out.
That's a fascinating, kind of worrying idea. Okay, so balancing real and synthetic data is tricky. What does all this mean for someone actually building an AI app now? When should they go through the effort of fine-tuning a big model versus using something like a retrieval augmented generation or RAG system? Feels like two different approaches to adding knowledge.
Yeah, it's a really crucial decision builders face constantly. Fine-tuning, that's usually pretty resource-intensive, takes time and data. It's best when you're dealing with behavior-based failures.
Behavior-based? Like what?
Like if your model just consistently fails to follow instructions for the output format, maybe it generates HTML that doesn't work, or it doesn't adopt the specific persona or tone you need. You're teaching the model how to behave. It's like teaching your chef a whole new cooking style.
Okay, so fine-tuning is for style and format. What about RAG-AG?
RAG, retrieval augmented generation. That's more for tackling information-based failures. This is when the model gives answers that are factually wrong or just outdated because it doesn't know the specific current information. RAG works by fetching relevant information from an external source like a database or the web and giving it to the model along with the user's query. It's like giving your chef a specific up-to-the-minute cookbook for the question asked.
And you said RAG can sometimes be better.
Yeah, here's a surprising thing. For tasks involving really current events or specific factual recall, RAG systems can often outperform fine-tuned models. Because they access live information, they don't rely on the model having memorized everything, which it often haven't.
That's counterintuitive, but makes sense. What about making fine-tuning easier?
Right, there are techniques for that too. Parameter-efficient fine-tuning, or PEFT. Things like LoRa are really popular. LoRa lets you customize a huge model by only training a tiny, tiny fraction of its parameters. Much faster, much cheaper. And there's also model merging, where you kind of cleverly combine the specialized skills of different fine-tuned models. These are great for multitasking or getting models small enough to run on a device.
Okay, so you choose ARG or fine-tuning based on the problem, but even the best model is kind of useless if it's incredibly slow or costs a fortune to run, right? Especially at scale. How do we make these AI applications fast and, cost-effective? It can't be like a 5-star restaurant that takes an hour per customer.
Absolutely. Performance and cost are huge.
Sure.
You need to understand the computational bottlenecks. During inference, that's when the model is actually generating a response. Typically for language models, there are two main phases. First is pre-filling processing the user's input prompt. That's usually compute-bound, limited by the raw crunching power of your hardware. like waiting for a powerful oven to heat up.
Okay, compute bound for the input.
Then there's decoding. That's where the model generates the output, token by token. And this phase is often memory bandwidth bound. It's limited by how fast you can shuttle data between the computer's memory and the processing units, like waiting for ingredients to arrive from a slow, distant pantry.
So different bottlenecks. How do you optimize for them?
Several clever techniques. One is quantization. You basically reduce the numerical precision of the model's weights, makes the model smaller, uses less memory, runs faster. Sometimes there's a tiny hit to accuracy, but often it's worth it.
Okay, making the numbers simpler. What else?
Speculative decoding is another neat trick. You use a smaller, much faster model to generate a draft response. Then the main, larger model just quickly checks and corrects it. This can give you huge speedups, maybe like 8x faster token generation for those drafts.
Wow, using a little helper model.
Yeah. And then there's continuous batching. Instead of waiting to fill up a big batch of requests, you process them more continuously as they arrive, packing them efficiently onto the GPU to keep it busy. Improves overall throughput. And finally, prompt caching. If you get the same or very similar prompts often, you just store the result and serve it back instantly. Saves a ton of computation and cost for common queries. It's all about making that kitchen workflow super efficient.
Fascinating how many layers of optimization go into just making it run fast. Okay, so we've got the models, the data, the performance tuning, the development process. Bringing all these pieces together requires a really well thought out system, an architecture. What does a robust AI engineering architecture actually look like? How do all these parts connect?
Right, it's definitely more than just hooking up a query to a model API. A production-ready system has several important layers, like different stations in that well-run kitchen. So first, beyond the basic query API interaction, you often have context construction. This is where you add extra information to the user's query before sending it to the model.
Like the AURA pattern we talked about.
Exactly. That's a key tool here. Fetching relevant data from databases, maybe doing a web search. It's about giving the AI chef all the right ingredients and background info for the specific request.
Okay, context first. What's next?
Guardrails. Absolutely essential. These are checks and filters to mitigate risks. Things like preventing the model from accidentally leaking private information, maybe by detecting and masking sensitive data like a phone number, replacing it with phone number, and also blocking harmful or bad prompts. But you also have to be careful and track your false refusal rate. You don't want the guardrails to be so strict that they block legitimate conversations.
Finding that balance makes sense.
Then you often have routers and model gateways. Routers look at the incoming query and decide where it should go. Maybe to this model, maybe that tool, maybe a specific RAG system. They often use intent classifiers to figure out what the user wants and can gracefully handle out-of-scope conversations. You know, if someone asks your finance bot about the weather, the router sends it somewhere else or gives a polite refusal.
And model gateways.
They provide a single unified interface for your application to talk to potentially many different underlying AI models, maybe from different providers. Simplifies the code. And finally, caching. We mentioned prompt caching for performance, but you can have exact cache for identical queries and also semantic caching, which tries to match queries that are similar in meaning.
Semantic caching sounds powerful.
It can be, but honestly, its value can sometimes be dubious. It's complex to implement well, and deciding if two queries are truly semantically equivalent enough to reuse a cache entry can be tricky and sometimes lead to subtle errors. So use with caution.
Okay, that paints a really clear picture of the whole system architecture, but once it's all built and running, how do we know if it's actually any good? I mean, beyond just, eyeballing the results or hearing anecdotes, how do you evaluate these complex AI systems systematically, like a proper food critic?
Yeah, evaluation is tough for these big foundation models precisely because they're so open-ended. A lot of teams still do just eyeball the results, which isn't ideal. To be more systematic, we look at metrics. For language models, there's perplexity lower is generally better, indicating the model is more confident or accurate in its predictions. We also use functional correctness evaluation. This is like running unit tests, especially if the AI generates code or structured data. Does the output actually work? Does it compile? Does it match the required format?
Verifying the output does what it should.
Right. And there's semantic similarity, using those embeddings we talked about earlier to measure if the meaning of the AI's output is close to a desired reference answer, even if the exact words are different. And one really interesting area now is using AI as a judge. Basically, using one AI model to evaluate the quality of another AI model's responses.
AI judging AI.
Yeah, it offers amazing speed and scalability for evaluation, but, and this is a huge caveat, do not trust any AI judge if you can't see the model and the prompt used for the judge. You need transparency there. And ultimately, remember this, you don't really care about which model is the best on some generic leaderboard. You care about which model is the best for your specific application.
Right. Context matters.
Exactly. Those public leaderboards can be useful, but they can also be misleading because of data contamination. The benchmarks might accidentally contain data the model was already trained on, inflating its score. So the best practice is to design your own evaluation pipeline. Define clearly what good means for your use case by tying evaluation metrics back to actual business metrics.
Can you give an example?
Sure. Maybe improve factual consistency in a customer support bot directly leads to a measurable increase in the percentage of issues resolved automatically. That's a business metric. And then, crucially, you need to be constantly annotating evaluation data drawn from your real production traffic. That gives you the ground truth for how your system is performing in the wild.
Okay, tying evaluation to real-world impact. And finally, there's the human element again. How do the actual users help the AI get better? What's their role in this loop? Like diners giving feedback.
User feedback becomes even more important with AI than traditional software. It creates this virtuous cycle, a data flywheel. Because in the age of foundation models, unique, proprietary data is more valuable than ever. That feedback is proprietary data. We distinguish between explicit feedback, the classic thumbs up, thumbs down button, and implicit feedback.
Implicit? Like what?
That's gleaned from how users interact. Did they stop the generation halfway through? Did they immediately rephrase their query? Did they copy the answer? These are signals about satisfaction. And there are different strategies for asking for feedback. You might prompt the user when the model clearly makes a mistake, or maybe when the model itself indicates low confidence in its answer. Sometimes you see systems showing comparative options, like Google Gemini sometimes does, showing two drafts side by side and letting the user pick the better one. That's great feedback.
But user feedback isn't always perfect, right?
Definitely not. You have to be aware of biases in user feedback. There's leniency bias. People tend to rate things more positively than maybe they should, perhaps to avoid feeling critical. And sometimes it's just randomness if users aren't motivated to give thoughtful feedback. So you need strategies to filter and weigh user feedback appropriately to really make the AI chef better based on what the diners are truly saying.
What an incredible journey today. We went from the absolute smallest level, the world of tokens and embeddings like the raw ingredients and their essential flavors, all the way up to the complex layers of AI engineering architecture, the whole bustling kitchen. It's really clear that building AI isn't just a one-time thing. It's this constant cycle, isn't it? Learning, building, refining, a lot like a great culinary art, always evolving.
Absolutely. And the thing is, this whole field of AI engineering is moving so incredibly fast. The tools, the techniques we talked about today, they're really just the start. The constant challenge, but also the opportunity is going to be needing to continuously learn, adapt, refine how we build these things, especially as the AI models themselves keep getting smarter and changing. So the final thought maybe is, what does this mean for your role in this rapidly shifting landscape? How will you, the listener, engage with this evolving intelligence, whether you're building it, using it, or just trying to understand it?